Welcome back, everybody, and we're going to start off this next part of section 16.2 talking about integrating in a certain direction. And before we do that, let's review the kind of line integrals that we talked about in section 16.1. So if we have a multivariable scalar function, this could be a function of 2 or 3 variables, or really as many variables as you want, but the idea is it's a scalar function, not a vector field, and we want to integrate that over a curve with respect to arc length. Or ds is respect to arc length. Then the way we do that is we need to find some parameterization for this curve. The parameter value t goes from a to b, so we integrate from a to b the function just defined on that curve times the magnitude of the derivative of the parameterization dt. And this is what we saw in section 16.1. But what if, instead of taking an integral with respect to arc length, we just want to take an integral with respect to a specific variable? Then what we get are these integrals. So now I'm assuming that my function is a function of 3 variables. If I want to integrate that function over a curve just with respect to x, I still need that same parameterization, r of t, and I plug that into my function. So now I'm saying that r of t equals x of t, y of t, z of t. I'm still integrating from a to b, but now this dx becomes x prime t dt, and this x prime is the derivative of the first component of r. And so that's my dx. If I want to integrate with respect to y, it's the same. The only thing that changes is now dy is the derivative of the second component of r, dt. And dz is z prime, or the third component of r, the derivative dt. So instead of taking a magnitude of the derivative, so that would be these derivatives squared, added together, and then a square root, I just take the derivative of each one of these, depending on which direction I want to go. If this was a function of 2 variables, so f was just a function of x and y, then I could integrate with respect to x and y, and the only thing that would change is there would be no z term there. R would just have 2 components, an x component, a y component, and I take the appropriate derivative depending on which direction I want to integrate in. So visually, let's take a look at what's going on. So we're going to take a look at a function of 2 variables. Let's say this is our curve in the xy plane. That's our c. It's a smooth curve. Then, so if I wanted to compute this line integral, as we did in section 16.1 with respect to arc length, then what I'm computing is, let's say this top curve are my function values on the curve C, and I get this kind of ribbon out here above the xy plane. The area is this integral with respect to arc length. But if I just want to integrate in a particular direction, I'd say I'm only integrating this function with respect to x, then I'm just looking at this curve in this direction. So I might only see something that looks like this. And so this is the area I get if I integrate with respect to x. And with respect to y, I just look straight in this direction, and I might get a curve that looks like that. It's the same function, I'm just integrating with a particular variable, and this would be the area that I get for this integral. So it's almost like I'm taking this integral with respect to arc length, and if I want to integrate in a particular direction, I don't get this area of the ribbon, but I project that in a certain direction and compute the area that I get. Now, this also applies to vector fields, as we saw at the end of the last video. If I compute the dot product for my vector field line integral, then what I get are basically these three integrals added together, where now this isn't the same function over and over again. These are the components of my vector field, right? This would be my p, my q, my r. So these integrals in certain directions also apply to vector fields, but now the idea is we're only integrating a single component of our vector field. So for instance, if I just wanted to look at integrating the first component of a vector field, I would get an integral that looks like this. And so you'd only be looking at integrating how that vector field is acting in the x direction. And it's the same thing for the other 2. Okay, let's move on to doing an example. So let C be a circle of radius 3 centered at the origin, which is traversed counterclockwise. So we're going around this way. and we want to find this integral over c of y dx plus x plus y dy. So there's really two integrals here. One we're integrating with respect to x, one we're integrating with respect to y. Now the first thing we need to do is parameterize this circle. So I didn't give the parameterization to you, so we have to figure out what it is, and we can do that since it's a circle centered at the origin of radius 3, it's in the xy plane, and we're going around counterclockwise. It can be parameterized as 3 times cosine t, 3 times sine t. If you had another circle centered at the origin with a different radius, the radius is just the constant in front of cosine sine. And now t goes from 0 to 2 pi. So we're starting here, we're going around the circle counterclockwise, we stop here. And if you want to check this, that this works, if I plug in 0 for t, I get the point 3, 0, which is my starting point. And you start plugging in angles going around the circle. Pi over 6, pi over 4, pi over 3, pi over 2 is going to get you here. You can see that I'm actually going around the circle. So that's our parameterization. So what I really need to have dx, I need x prime dt, dy I need y prime dt, so I'm going to separate the two components of this parameterization. X of t is 3 cosine t, so it's dx is negative 3 sine t dt. Y of t is 3 sine t, so dy is 3 cosine t dt. And t still goes from 0 to 2 pi. So now if I want to put this integral together, the integral over the circle of y dx plus x plus y dy, for this y I need to plug in y of t. So instead of y I get 3 sine t. Then I need dx, which is x prime dt. So I get negative 3 sine dt. So 3 sine t, negative 3 sine t dt, this entire product here is y dx. Next I have x plus y, so 3 cosine t plus 3 sine t, there's my x. dy is 3 cosine t dt, and so this entire product is x plus y dy. Okay, and I'm integrating from 0 to 2 pi because t goes from 0 to 2 pi. Now simplifying things out, I can multiply together, distribute, and factor that dt out. So I, instead of having two integrals, just treat this as one integral with a dt at the end, and I get negative sine t squared plus 9 cosine squared and 9 sine cosine. So in order to start integrating this, I need to use some trig identities to make this easier to handle. So here are some trig identities that maybe you once knew, or perhaps you still know. But just in case, cosine squared I can replace with 1/2 plus 1/2 cosine 2 theta, or in this case it would be cosine 2t. Sine squared I can replace with 1/2 minus 1/2 cosine 2t. But in this case I'm not going to do either of those. But these two identities show you that cosine squared plus sine squared, if I add these two together, these terms cancel out, I just get 1, so cosine squared plus sine squared is 1. And if I do cosine squared minus sine squared, so I subtract these two, then the 1/2s cancel out, I add these together, and I just get cosine 2t. And that's what I'm going to use here. If I look at these two terms, I factor out a 9. I have 9 times cosine squared minus sine squared. So I'm going to use this identity. I'm also going to use that sine cosine is equal to 1/2 sine of 2 theta, or in this case 2t. And I'm going to use that to take care of this term. So I use those trig identities, and these two terms become 9 cosine 2t, and this term becomes 9/2 sine of 2t. And now I can integrate these things. From here, you're going to want to use a u substitution for 2t, and I'm not actually going to write the u substitution out. So if you're more comfortable writing the u substitution out, please do so. Hopefully you have a paper and pencil with you. You can pause the video, work it out, writing u equals 2t, so then du is 2 dt, and go from there. Either change your bounds or wait to substitute at the end. But this u substitution of a constant times your variable happens a lot. It happens so often that I'm not going to rewrite it. If you have a u substitution that's a constant times your variable, all you need to do is integrate the function as you normally would and divide by the constant, right? Because if u is k times x, where in this case our x is our t and k is 2, then du is k times dx. So if I substitute u for dx, then dx is equal to 1 over k du, right? So if I have this integral, I'm really just dividing by this constant, and I get the integral with just the u. So really all you need to do is integrate and divide by whatever constant's there. So what am I going to do? I'm going to integrate cosine. If I integrate cosine, I get sine. And then I need to divide by 2, because that constant is there. So I get 9/2 sine of 2t. And I integrate sine, I get negative cosine, and I need to make sure I divide by 2. So I get negative cosine, and 9/2 becomes 9/4. And now I evaluate from 0 to 2 pi. And my answer ends up being 0, right? So both of the sine terms become 0. Negative 9/4 cosine 4 pi, that's just negative 9/4. Then I have 9/4 cosine 0, which is positive 9/4. They cancel out, and 0 is my answer, which is okay. Before we move on to the next idea, just like in the last video, if I change the orientation of my curve, I need to change the sign of my integral. So if I'm integrating with respect to a single variable, so right here I have dx, it could also be dy or dz. Let's say this is my curve, I'm integrating from a to b, I'm going in this direction from a to b, and then I decide I want to switch the orientation. For some reason instead I start at b and go towards a. I call that curve negative c. Then the sign of my integral changes. You can think of when you were first learning integration, if you switched the bounds of integration, you had to multiply by -1. That's kind of similar to what we're doing here. I'm switching the orientation of my curve. I have to multiply by -1. And again, I have it written for dx, but the same happens for dy or dz. And we saw that was true for line integrals of vector fields. Now, if I'm integrating with respect to arc length, we talked about this when we talked about section 16.1. I switch the orientation of my curve. The integral is exactly the same. Because now I'm not changing directions if I'm integrating with respect to arc length. I'm integrating with respect to the length of the curve. If I change directions, the length of the curve is still the same. So I don't have to multiply by a negative if it's arc length. Or you can go back to how you actually calculate these things and realize that if you plug in a negative parameterization, you switch the sign of your parameterization, the integral itself doesn't change at all. Whereas if you switch the sign of your parameterization for these, you do have a negative that pops out. Okay, before we go, I want to talk about another application of line integrals, of vector fields, but it's exactly the same as in the context of work. The formula is exactly the same. We're just calling it flow and circulation now. So if I want to integrate a vector field over a curve, it's f.dr, where we're integrating from a to b, where these are the endpoints of my parameterization, plug the parameterization into f, dot with r prime. This is what we saw previously. But now we're going to say that f represents the velocity of a fluid. And we call this integral, instead of calling it work or some other name, it's called flow if the curve is an open curve, meaning that it has distinct endpoints. It's called circulation if it's a closed curve. These are details I don't think we need to worry about, but just to make sure we have the definitions. What is important is the difference between an open and a closed curve. This is going to come up again later. So an open curve has distinct endpoints. It's say I start here and stop here, they're different points. Or I start here and stop here, those are different points. That's an open curve. A closed curve, you start and stop at the same point, so you make a loop. I mean, that's the simplest way, right? I start and stop here, so I go around once, that's a closed curve. Here, I go around this crazy shape. I stop where I start, that's a closed curve. All right, let's finish with an example. So find the flow of a fluid whose velocity is given by x, y, y, z, z, x along a curve, and we're given a parameterization for this curve, t, t squared, t cubed, and t goes from 0 to 1. Okay, so I'm given the a and the b here. I integrate from 0 to 1. All I need to find are the vector field defined on the curve and the derivative of the parameterization, and then dot and integrate. So first let's look at the vector field on the curve. Everywhere I see an x, I plug in a t. Everywhere I see a y, I plug in a t squared. Everywhere I see a z, I plug in a t cubed. So x times y becomes t times t squared. Y times z becomes t squared times t cubed. And z times x becomes t cubed times t. So that's t cubed, t to the fifth, t to the fourth. That's my vector field on the curve. And then r prime, just take the derivative of this vector function, 1, 2t, 3t squared. And then I set up my integral. It's the integral from 0 to 1 of t cubed t to the 5th t to the 4th, dotted with 1, 2t, 3t squared. I compute the dot product, t cubed plus 2t to the 6th plus 3t to the 6th, right? T cubed times 1, I get t cubed, plus t to the 5th times 2t to get 2t to the 6th, plus t to the 4th times 3t squared to get 3t to the 6th. And now this is just a Calc 1 problem. Before I integrate, I can combine these like terms to get 5t to the 6th. Then I integrate t cubed to get 1/4 t to the 4th. I integrate 5t to the 6th to get 5/7 t to the 7th. Plug in 1, subtract and plug in 0. I get 1/4 plus 5/7, which is 27/28. Okay, that's it for now. We'll return with the conclusion to section 16.2 in the next video.